The SDXL toolchain allows the user to specify the computational kernel to accelerate an FPGA in different ways. As we know, SDXL supports kernels written in C, C++, Register Transfer Level or RTL, like Verilog and VHDL, and OpenCL. While C, C++ and RTL were already supported in Vivado HLS and Vivado, respectively, OpenCL is a prerogative of the SDXL toolchain. This addition allows to widen the range of possibilities to develop a kernel for FPGA, as well as the final users. The rationale behind this choice is therefore quite simple. Now users, according to their skills and familiarity with the hardware design flow, can develop efficient FPGA kernels by leveraging the language they are more confident with among the ones supported. A rationale so simple is also very smart. In fact, within this context, this approach allows to target not only the hardware designers who are already proficient with RTL, but also software developers who have never used an FPGA before. And this is obviously bringing FPGA technologies to more users than ever before. For instance, in case of OpenCL, a software developer, instead of starting from scratch, can exploit the portability of OpenCL code among multiple platforms and evaluate a first design. Of course, remember, the portability of code does not imply the portability of performance. The heterogeneity of supported languages enables users to, potentially, implement different versions of the same kernel in different languages, and evaluate the goodness of each design as well as the suitability of a language for a given computation. As a result, users can choose the best implementation according to multiple metrics like performance, resource, usage, or design time. As an example, in order to fast prototype a kernel, the user can exploit either C, C++, or OpenCL. This provides a first approximation of the achievable performance. The user can then optimize the current design or implement it on RTL to have a complete control of the design and reach the maximum performance. Of course, implementing a design in RTL is a way more complex and time-consuming than C, C++, or OpenCL. As you can easily understand, basically, it is all a matter of trade-offs among performance, area usage, and development time. Therefore, the starting language significantly depends on the skills and expertise of the designer. Moreover, supporting different languages allows SDXL to be accessible by a wide range of users, from hardware developers to pure software engineers. On one hand, hardware developers will rely on RTL or C, C++ to design their kernels, while pure software developers will take advantage of C, C++ or OpenCL. As a result, SDXL makes hardware acceleration on FPGA accessible also to non-hardware designers. This is a key picture for SDXL. It is shown the SDXL design flow. We are going to use it several times, but always providing a different way of reading it according to a specific need. As you can notice, the input kernel may be in C, C++, RTL, or OpenCL. From a design flow perspective, the choice of a language has a little to no impact on the overall flow. Independently from the chosen language, the user has to implement the host code relying on the OpenCL APIs. Purpose of the host code is to manage the application runtime, initialize the OpenCL device, create the memory buffers, transfer them from the OpenCL, and start the FPGA execution. According to the chosen language, the user has different options to design and optimize the kernel. In case of a C, C++, or OpenCL kernel, SDXL provides many different directives to improve the kernel design, like loop and data storage directives. On the other hand, an RTL kernel requires the user to take care of every low-level aspects of the design, and of course, the kernel design has to be compliant with OpenCL computation and memory model. Once satisfied with the implemented design, the user can simulate its behavior by means of both a software and hardware emulation. Software emulation is not available for RTL kernels, since no high-level synthesis process is required. We already have a hardware description. As a consequence, the hardware emulation is the only emulation available for every supported language. Finally, when the design is ready and passes the emulation step, The system-built functionality, independently from the chosen language, automatically performs all the steps required to generate the bitstream, as well as the host binary to manage the OpenCL runtime.